So in this video, which will hopefully be just a quick one, we're just going to define what a group is. Right, so what is a group? A group is a set, we'll define this in a moment, with the binary operation again, we'll define that in a moment and call this star. So what is a set and what is a binary operation? So a set is just a collection of things. So for example, 1, 2, 3 is a set. 1 and 2 is a set. And in fact, this is a subset of this. So we might write this. So are the set of all natural numbers, i.e. counting numbers, and the set of real numbers or complex numbers. There's also the set of all cats in the world, and a subset of this may be the set of cats in London. So these are just some examples of sets, and you can have pretty much anything you like. Next we need to define what a binary operation is today. Well, a binary operation acts on a set. Well, it acts on elements of a set, rather, is the way to think about it. And it's a function or a mapping from G cross G back into G. And note the fact that because this lands back in G, what we say is that star has closure. And this will become apparent again in a moment. But what we might think of this is as if I take a G in big G, the left one, and a H in G, sort of from the right one, then we can combine G and H, and it will still be in big G on this side now, where this is sort of a new element of G. So for example, some might be addition on the integers. So you might have addition from Z cross Z to Z. And so 1 plus 2 is 3. So here 1 was in the integers, 2 was in the integers, and combining them with the plus is 3. So the same would be for multiplication and division in the real numbers, for example, as well. So that's a binary operation, and that's a set. But there is a little bit more to the definition of a group. In fact, there are 4 more things we assume. Well, with the caveat of some people will write 4 and some will write 3. And we'll explain that now with number 1. There is closure, which, as we just mentioned, is part of the definition of binary operation. So actually, if this star is a binary operation, we will have closure every single time anyway. But this is to say, for any G and H in G, G star H is in G. That's our first one. Now our second one is the existence of an identity element. And we will call this E. And E needs to be in the group G, and it needs to satisfy that combining it using the binary operation with any element of the set gives back the same element. And this should be for any G in G. So for example, this might be 1 with multiplication, multiplying 7 by 1 gives back 7, and in fact it works for every number. Or it might be addition with the number 0. So, or maybe if you're rotating a shape, it will be the rotation that does nothing. So that's the identity element. We have 2 more. On to 3. We have inverses. Which is to say that for any G in G, there should be an element H such that combining G with H will always give you back that identity element we just said there must be. So for any G in G, there should exist H in G such that G composed with H equals H combined with G equals the identity. Now one of the things you might be picking up on is that I've written G combined with H and H combined with G. And you might be asking, why have I written both of these and not just G combined with H? And that's because actually these might not move around, or the official term is commute. And see, if we're doing addition or multiplication, we're used to things commuting, i.e. being able to swap them and it making no difference. But if you say work with division, 7 divided by 3 is not the same as 3 divided by 7. And so there are cases where operations don't move around or commute. And that's why we have to write this. As for the last part of the definition, what have we got? We've had closure, we've had identity, we've had inverses, and now we have associativity. Now if you study algebra further, associativity is one of the most appearing things in all of algebra. And that's to say that if we take any G, H, and K in G, then it doesn't matter really what order we apply star in, which is to say that if we apply star to G and H and then to K, it should do the exact same thing as applying G to H applied to K. So these brackets tell you apply H to K first and then combine with G. This says combine G with H but then apply K. Notice the order has to be the same. It has to go G then H then K, G then H then K, but the brackets can move. Right, so those 4 things are the definition of a group, and thank you for watching.